Hey everyone, what's up? Good to see you here, Kayla. Good to see you here, Charles Fleming. We got some stuff right here. President's approval rating, good stuff. Cassandra, good to see you here. Charles, Brianna. Wow, we got everybody. Let's throw out some voice. Mubot, you awake? I don't think Mubot's awake. Here, let's watch an intro and Mubot wakes up. Here, intro, then time for class. Or we're back now, getting it loaded up. Love the intro. I do too, Brianna. I was like getting things loaded up in the background here. Can you post the assignment? Is it not posted? This is for 320 right here. Whoops. Did I not post it? Whoops. Make sure it's posted right here. Let's go get that model building posted. Is it not posted? Then we're going to do some 201. It should be, it says due May 6th. That's the activity. Oh, I'm looking at the activity. I don't even know what I'm doing. I don't know what I'm doing. Do you know? I don't know. Where is it? Assignment, model building. Oh, there it is right there. Okay. Let's go post that assignment. Let's put it due out here on... We usually have things due on Sunday, right? So May 8th. May 8th, this is a bonus assignment. Save and publish. I think will be good right here. May 8th. Let me see. 2 seconds here. I'm going to get this posted right here. Thank you, everybody. Gonna post. Changing dates. But how's everyone doing today? Getting a little work done right here. Model building. Okay, gonna post, insert, document, upload document, model building, post. Kayla, you should see it. No, you're good. Thank you for telling me. I thought it was posted. I thought I had it up. I must not have done that. I think sometimes I do things and I don't do things. So that's what happens. Brian, you aren't feeding the bunnies right. Oh, no, there's no Rice Krispies in that box. Leftovers day, no cooking for you. Oh, no, Kayla. I made some enchiladas last week for our 1 week anniversary on Saturday. Some enchiladas. Well, I bought a thing of enchiladas and put it in the oven. It counts, right? Still counts. Enchiladas in the oven are good, whether you make them or not. Better to make them. Probably not that hard to make enchiladas. Like, I'm not downplaying like making enchiladas, but I'm the one who did it. I think we'll do it tomorrow evening. Does that sound good, right, Kayla? Good stuff. Let's see, the 800 selected adults, presidential approval ratings. We got presidential approval. Stat 201, chapter 16, quiz, presidential approval. The alpha level. That's a good one. I love that one. Chapter 16 quiz. Alpha level. And what else? Homemade enchilada sauce is so much better. 1 week already. Wait till 1 month. I know it, Charles. 1 month anniversary. Gotta do the 1 month on the 23rd of the next month. So exciting stuff. We are getting the assignments open. They're working on roofs across the street. Settings. I don't want the settings. What the assignment? I want chapter 16 assignment. Okay, presidential approval rating. My anniversary is 23rd. Oh, of October. Congratulations. Before lending money, bank question. You bet. Put the bank question on here. We did that one earlier and we did it yesterday too, but Charles, we can definitely do it right here. It's a good walkthrough question on type 1, type 2 error, alpha level, sample size. So the bank loans. So I'll put that right there. Hey, Shreya, good to see you here, Shreya. Newbot saying hey in the chat. Got to throw out those points. Well, so we're going to do the first one we have on the list is the presidential approval rating. So let's go find that presidential approval rating. Ah, we found it. Okay, let's head over here to the main screen and do it. Put in the timestamp in. So what is the first thing we do whenever we get to a problem like this? You know it. Someone's got to say it, though, because when you get to this... No, Andrew, no. Andrew, I'm sorry. Oh, no worries, Charles. We're going to do it here, too. What is the first thing we do when we get to a problem like this? What is the first thing we do? The very first thing we do. Yeah, ask some 320s. Yeah. Very, very first thing we do. Very, very first thing we do.
Notation, brother.
Very first thing we do is notation. So what notation do you see on here? What notation do you see? What notation is there? We need to mark all the notation. Andrew, so good to see you. You got this, man. It's one of the hardest things when I finished school. I was applying left and right, and I had this job turn me down that I didn't even want. And I was like, the job I don't even want turned me down. Drove me nuts. That's why I'm here today, crazier than ever. 800, Kayla doing a great job. 800 is sample size. I'm going to write the equation right here. It's a huge help, but the problem is you wouldn't know. 45, oh, wow. Great job. Close, Kayla, close. That's not P yet. Andrew, man, I feel for you. That's not quite P, because this is from a poll. So from a recent poll, which polls are samples. So good. This is not quite P. That is not quite P because that came from a poll, which comes from a sample. Not quite. X is the number of successes. X is how many successes we would see. So that is P hat, which is the sample proportion. And this is the good practice. Don't worry. And don't worry, Kayla's practicing some more stat to one. That is the sample proportion, which means once we find P hat, we find Q hat because they're complements of each other. So Q hat is just 1 minus P hat. So we know that Q hat is going to be the complement of P hat. So just remember they add up to 1. And once we get P hat, we can get Q hat. And that's how we get it. Now, the only other thing we need to solve this is going to be what? Just notation-wise, what is the last thing we need to solve this problem right here? The last thing we need to solve for the 1 proportion Z interval is going to be a what? Inherent in the name. The 1 proportion Z interval for a few occurs. Yeah. Yeah, that's tough right there. That's why, like, I don't want to move. I want to be back in Knoxville. I'll be back. Do we multiply 0.47 by n? Well, no, you do P times Q over n square root. And then we got to find the Z-score. Does that make sense, Swimming? No worries, Swimming. 100 points right there. We're going to go find the Z-score right here. To find the Z-score, we're going to go between and mark a certain area. So the between and tell the area we want. It's going to be 95% right here. So that's 1.96. Classic Z-score. You can get other ones by putting in the numbers and finding the Z-score, which is the amount of standard deviations you'd go out on the normal curve. You can see right here, 1.96. Very close to 2. Make sure to use 1.96. So make sure to use the proper Z-score to get it. So because it's 95% confidence, we're shading the middle 95% of the curve. And the middle 95% of the curve has a Z-score of 1.96. And that's for the middle 95% of the curve shaded in is positive and negative 1.96. And identifying the numbers is the key to these problems, because once we have all the information, we can go in here and do 0.48 plus or minus 1.96 square root 0.48 times 0.52 over square root over 800. And we are just plugging in our numbers from up above. So that's P hat right there. That's P hat right there. That's the Z-score right there. And, oh, we did this N as this. And then last but not least, we need this. Now, I always like to make it clear that everything I'm marking in here is the what. This is what I usually solve for first. Everything in that green box is known as the what. Like once we say plus or minus on an interval, everything in the green box is known as the what. Everything in the green box is known as the what. The margin of error. Great job, Andrew, getting everyone 100 points. Great job, Andrew, right there. So this is the margin of error. It's the plus or minus on an interval. And then the center right here is the middle of the interval. So that's going to be the estimate, which is our best guess. Because if we saw this in a poll, we're like, well, that makes sense. That's probably what it's close to. And then we need a margin of error. Not me coming in. Yes, that's awesome, Maria, right there. 100 points, Maria. Oh, no, I clicked the lights button. What am I doing? So we're going to go right here. It's a big margin of error. And there we go right there. So the center of the interval is very clearly 0.48. But we have to solve that margin of error right there to figure out the width of the interval. Well, half the width is the margin of error. So let's go solve that. Okay, so mathematically speaking, we've got 0.48 times 0.52. That's the top. Divide by 800. This quantity right here that we've just found by solving that is known as the standard error. Now, that's not the margin of error. I did square root it, right? I did. So that's known as the standard error. Standard error is p hat times q hat over n square root. When we multiply it by 1.96, we have now achieved the quantity known as the margin of error. So that quantity right there, which we solved for mathematically, there's the numbers plugged in, there's the solving of it. It rounds to 3.5, and this is a rounded problem, so we should be good to round that to 3.5%. There's the 3, there's the 0.5, rounded when you round up. So 3.5. Let's take a look. So plus 3.5. It's decimal 0.035, but percent 3.5. So what is the upper bound of the interval? The upper bound is the number at the top of the interval, as we can say that we are 95% confident that the presidential approval rating is contained in this interval. I'm 95% confident that the true presidential approval rating is contained in the interval. And so what is the upper bound of the interval? Just think how this interval works with the symmetric up, the symmetric down, and just put in the chat like what the upper bound of the interval is. What would be the upper bound? We call it the upper limit or the upper bound, the UL, the CL, the upper limit, the lower limit of the confidence interval. There's the center and there's the lower limit. Well, we'll get into it today. Oh, just ask a question. Just say, let's start the thing. Let's start the assignment, Kayla. Say, hey, Brian, how about we just start this? How about we just take a look? How about we just start it? Who knows what the upper bound would be? So we just take, and we're going to add on this value right here, and that's going to get us to the upper bound. So we need to add, great job, Andrew, right there. And then the lower bound is going to be the same where we subtract it. So as long as my brain's working properly. There we go. You got it, Charles. We got this 44.5 to 151. So round to 3 decimals, 44.5. I think we did this right. I think so. So this is where it gets interesting. They think 48% is true. I do all the questions. We could start it. I'll put start on it. If they think 48% is true, just tell me this. Do you think they're justified in thinking 48 is true? Why or why not? Now, this is technically P0 right here. They are hypothesizing that 48% is true. Hopefully I said 48 right there. They are hypothesizing that 48 is true. So we didn't mark this as notation, but that is what they are hypothesizing. Yeah, exactly. And that's the whole thing. It falls and it's in the interval. It's contained in the interval. So that is a believable. It's at the center of the interval. So it's like, if someone says, I think the president has a 48% approval rating, you're saying, why do you think that? And they say, well, recent polls showed 48%. You'd say, well, that's believable. Meebot loving some randomness right there. Random question, somebody would Project 2 live stream from... I wouldn't use the live stream. Nicholas, we got some really good advice for you right here. Random question. Meebot loves randomness right there. You say randomness, and Meebot kind of freaks out, Nicholas. Good to have you here, Nicholas. Let's show you some points. I'll answer your question here, and I'll show you some great links for that, Nicholas. So I'm going to give you a link to a video that pretty much has everything you need in a second, so check it out. Based on this, we would not reject it. We'd fail to reject it. It's contained in the interval. So your number one, here we'll do this advice for Project 2. We're going to go here and go to advice for Project 2, Stat Tool 1, Project Help. It's going to be a quick section right here. So we're going to do a really quick section right here. We've got another one. I would love the poll. Like, it's 600 people, an accurate representation. Yeah, getting a good answer there, Andrew. Getting an accurate representation or a representative sample from 600 people would be really tough. That'd be really tough to say it's a representative sample. It's like, is it? Really? So, here we go. Let's check it out. So we're talking a little project help right now. So Nicholas, for the project, the number one suggestion I have, we've got a few videos. I'm gonna add some timestamps to them. So with this right here, let's check out stat 201 UTK, and let's go here. We're gonna put out some videos right here. Okay, videos. There we go. And there's the office hours from this morning. We're gonna go into here. We're gonna add the timestamps. So going right here, the morning timestamps. Edit video. There's the timestamp. So this morning we covered the future research. So I wouldn't necessarily. The morning video is decent. Oh, it's gonna play in the background. So here's where we did future research this morning. Oh, starting it up right here. So we'll put future research right here. If you're looking at the chat, you'll see it. There's future research video. But then the real big help is going to be May 1st right here. We covered all the jump work right here. So all jump questions. And then we did one on we did the executive summary. How's Chelsea do it? Did she? Yeah. And we're married, Andrew. I got married 10 days ago. I forgot. Saturday, Sunday, Monday, Tuesday. 10 days ago, I got married. I am a married man. Chelsea is doing great. I know. What's happening with the world? Brian's married. So yeah, didn't live stream it. There were requests from family too to live stream it. There were requests. Interesting fun. So I've been gone for like 5 months. No, come back, Andrew. Executive summary. And here's the executive summary. So there's links in the chat. If you click the links in the chat, it'll bring you to these videos. We plan to. That's the plan. Come back, get a nice house, enjoy our time, get some dogs. I seriously, when we get back to Knoxville, I'm like, we're getting a golden retriever. Not to be like those people with a golden retriever, but I'm just saying we're getting a baby golden, and it's going to learn to love the bunnies. We got 2 bunnies. So our baby golden dogs, you can get a golden retriever. It's going to learn to love the bunnies. And then we're just going to take all the Instagram photos of the golden snuggling the bunnies. Chelsea mustn't take you. Play pool. Kids are fun. Is that your suggestion, Kayla? Is we should get kids instead of dogs? We should be like, let's just have some kids. Is that the suggestion? Should we have kids, Kayla? Kayla, advise me on this. As a married individual, should we have kids? Thank you, Nicholas. And there's the links to the chat. Thank you for the congratulations. Where's out at Nicholas? We're gonna make you a mod right here. We're glad to have you here. Anytime you want to swing by Nicholas, we throw out those points and we have a good time here. We chat and relax and get some work done. Little Brian's running around doesn't sound so bad. Does the world need more Brian/Chelsea combos? The dogs equals kids. I can say that too. Sounds good to me. That's a bet. That's a bet right there. What's a bet? That she'll be back? That's awesome if so. We're going to do, so Caleb, we'll do one more 201. We'll do the alpha levels question. And then Charles, we can swing back and do the bank, but I'm going to put the 320 in here starting the next assignment. Assignment 12, right? Maybe? I don't know. I don't know what we're doing. You tell me what we're doing. BS 320. BS 320. Assignment 12. Starting it. Cool. It's a good assignment. I mean, they do the same things as dogs. You got to feed them and they... for a certain time period, I'd hope. UTK need the next generation of Brians. Oh my God. A literal tiny Brian. A literal tiny Brian. Is the world ready? I don't know. Maybe not. Probably not. Probably not. That's my answer to that. We are going to do the alpha levels question. It's a fun one. It's a good theory question. It helps you understand when to reject, not reject. And there's different versions of it. So it's a good one to do multiple versions of it. It's towards the end right here, right? Where's that alpha question? The alpha levels question. It's funny. I can tell you most every question for every, like, chapter. I can be like, oh, it's the this question. It's the this question. There's a lot of them. Where is it? It doesn't exist anymore. Really? I am trying to find it. I'm going to let you see. Official Tiny Brian. It just seems to be in 1-year-old voice. Great job. The official Tiny Brian. I like that right there, Shreya. Oh, I literally land on it. I was clicking back. It's question number 2 on this. So set over to the main screen and do this question. Testing full weapons, alpha level with weapons. Okay. No music in the background. Here we go over the main screen. Let's do it. The question. Yeah, awesome. For the define the parametric. Can we go over my question set first one? For each of the situations, define the parametric. Yeah. Can you? It's on chapter 16? We can do that one right there. You bet, Charles. Thank you, Charles. We'll make sure to do that one next. Awesome work, Charles. Okay. So a group is trying to find secret weapons or something like that. I don't know what's going on. Secret weapons, yada, yada, problem. And so with this right here, a researcher is developing scanners to search for hidden weapons at airports, has concluded that a new scanner is significantly better than the current scanner. They made their decision using an alpha of 0.05. Now, alpha is your level of what? Alpha is your level of what? Alpha is your level of what? Now, be very careful. This question is many versions. There's a lot of versions. So look at your version, map it out what I'm about to do. But alpha is known as your what? What are the names? What is alpha? We have to know what alpha is to talk about how to use it. What is alpha? Flip those back around. What is alpha? You can talk about, it's generally, we usually think of alpha, it's type 1 error. That is very true. It's type 1 error. It's relative to confidence level. Exactly. It's your level of significance that you're doing the test at. So alpha is known as the significance level. It's like what is your significance level? If p-value is less than alpha, reject the null. You can also do a confidence interval based on your alpha, do the two-tailed test. So there's analogous confidence intervals relative to a test done with an alpha level. I want to make this super clear. When you're talking about alpha levels, you're no, that's all right. Alpha does work with power, but the number one thing, it is connected to power. I can talk about that in a second. The number one thing to know with alpha is anytime you talk about your alpha, you're probably running a what? Because you're seeing if your results are significant. Anytime you talk about alpha, you're probably, the number one things you need to know is you're probably using it as a level of significance when you're running a statistical this. 4-letter word, the things you have to take in class. Anytime you're doing alpha, you're probably doing a statistical this, and you're saying this is the point at which I'm saying my results are statistically significant. P-values below this. Test right there, exactly. So it's a statistical test. Or it's the baseline for which we will say p-values below this are statistically significant. Unlimited power. So sounds like almost like Back to the Future with you can't use hoverboards on water. So you can choose your alpha whatever you want it to be. Now, we generally don't do wacky things like an alpha of 1.0, but the researcher has complete control of whatever they want alpha to be. Kayla is correct that when it comes to doing tests, alpha is connected to beta, as in alpha is inversely related to beta. And Kayla's also correct. Kayla's always correct that alpha is also positively correlated to power. If you increase your alpha, your test becomes more powerful. If you increase your alpha, you decrease type 2 error. But increasing your alpha would also increase type 1 error because alpha literally is type 1 error. Like your amount of type 1 error is your alpha level. So you're saying I will have usually what percent of results that are significant by random chance, as in I'm making an error. Like it's just random that these are significant. In most case scenarios, Most people use an alpha of what? That usually they're like, well, this is the amount of time I'll get a type 1 error. What is the usual consistent alpha? It's on the screen up there. What is the usual consistent alpha? Okay, it'll crack me up. What is our usual, like, I guess this is the amount of type 1 errors I'll make when I do, yep, 0.05. Unless otherwise stated, we usually use a 0.05 alpha. Once again, you can pick your alpha. There's a question later on that asks you, it's based on sample size. No. You just say, here's the alpha I want to use. Don't do something wacky like a 1.0 alpha. That's ridiculous. That's all type 1 error. Then your type 1 error rate's 100%. All type 1 error. That's bad. We don't like errors. So when we look at this right here, they're saying they used an alpha of 0.005. So we understand what alpha is now. Got a good little lecture on that. And so with an alpha of 0.05, they're setting the bar to the usual consistent level of here's where my alpha is. Now, it's said they found that the scanner was better. Now, be careful. Your question might be different. They found that the scanner was better. What does that mean for the p-value when they ran the test? It means they found significant results. I think it literally says the phrase, they found significant results, significantly better. So they're indicating something to you about what they found via p-value. They found that the scanner that they were testing was significantly better. It's lower than 0.05 exactly. So we know for certain, 100% certain, that the p-value, we don't know what it is. It just says that they found significant results, meaning if the results are statistically significant, it's lower than alpha. Tell me the range of values that the p-value would be contained between. The p-value has to be somewhere at this and up to this. And I think Shreya is saying it perfectly. It's Shreya, great job. It's less than 0.05, so it's got to be between 0 and 0.05, right? It can't be at 0.05 exactly. If it was right at it, we wouldn't reject, but it has to be below 0.05, 0 to 0.05. Shreya, excellent work right there. And once you graph this out, it's going to be a little bit easier to figure out the answer to this. They ask you two theoretical values, and the theoretical values, if I could speak, the theoretical values are going to be, that blue's the best. I think it said 0.01, and I think it said 0.20. Now, these are saying, like, what if they had used these alphas? So let's see right here. And be careful, there are many versions of this question, hence you want to draw this out. When you look at the way this looks, tell me, if this is your bar, is your p-value below it in all instances? Yes or no? There's where the p-value is, we don't know what it is. It's just somewhere below 0.05. Is the p-value below that bar right there? This bar. Put a big arrow towards it. Not that arrow. Is it below that bar? Yes, in all instances. So what would be your decision using this alpha right here? If you use that alpha, you would say, I would what the null. So remember, the p-value is down here. It's lower than alpha. So if you use that alpha, what would be your decision? So the p-value is lower than alpha. So what would you do? So you know what? The p-value is lower than alpha. The p-value is low. Blah, blah, blah. What do? Reject the null. Great job right there, Andrew. The p-value is low. I reject the null. P-value is lower than alpha. I reject the null hypothesis. So that's what we did right here. We said right here you would reject. And we say right here you would reject. Because the p-value is lower than alpha. Here's your alpha. Well, it said that they rejected right here. It said they found results. So we know it has to be below. And then since it's below the green line, well, it has to be below this line. But what about this line? We have two scenarios right here. If the p-value is in scenario A, here we'll do a different color. Let's say, because that's a hypothetical that the p-value could be down here. What would you do? If the p-value is in this area, what would you do using this alpha level? Exactly, enjoy that. If the p-value was down here, what would you do? Just hypothetical. I'm just saying, what if the p-value is 0.00001? And are we using alpha of this? Using an alpha of this, and the p-value is down here, you would reject again. So now we have that you would reject here, but the p-value could also be up here. And if the p-value was hypothetically up here, you would... So when you use this alpha level down here, what am I trying to express to you? That's the answer. If you were to use that lower... Oh, we want to put it over here. Well, if you were to use that lower alpha, then what's the conclusion about what we would do using the lower alpha? That's the answer to the question. Because the p-value is in this range. So, I mean, it could be above it. It could be below it. I don't know. Exactly. Well, if it's above, we would not reject. If it's below, we would reject. And it could be above. It could be below. I don't know. So the answer is I don't know. I don't know. The p-value is in this range, right? It's somewhere in that range. I don't know what it is. So you might reject, which was the same decision you made here, or you might not reject. This question has many versions. Do try to plot it out. And remember, you don't know what the p-value is. I think that's the hard thing about the theory of this question is you don't know the p-value. You're saying, well, it's below 0.05. So visualizing it right here can be a big help. Does this make sense, Charles, and everyone who's doing the 201 question right here? And great. I want to throw some 500 points. Thank you to Andrew and Kayla and Shreya right there helping out, participating. The practice is what matters. And these concepts come into play in a lot of classes. So thank you for everyone participating right there. And 201, let me know if you have any questions about this. We're just saying alpha is the point at which we reject. The p-value has to be in this range. So we know for certain we would reject using an alpha of this because the p-value is below that. But we don't know what would happen if we use an alpha of 0.01. So we would make the same decision for the question version I have. Be careful. There's a lot of versions of this question. The decision would have been the same at the 0.20 level, but it may have been different at the 0.01. Check answer. Woo! Scary, scary, scary. There's a lot of versions of this one. A lot of versions. No, never accept the null. We never accept the null hypothesis. So imagine this. Imagine this. Here, let's do a quick thing. Why do we not accept the null? Let's do it. Let's do a quick mini lecture on this, and then we're going to do 320. Never, never, never accept the null. And then, Charles, can you put that question you had again about the something? Give me the question again, Charles, you had. So that way I can do it. I want this one. We will do that one after the 320, Charles. I'm not putting a quiz. Sounds like you put a quiz on it. It's not a quiz question. I want people to see this, but check us out. Okay. You might think statisticians are crazy. You might think, Kayla, you are awesome. Thank you, Kayla and Charles right there. So you might think statisticians are crazy. But we never use the word accept something. We never accept. Accept implies finality to it. Let's say you're going to go buy a diamond. Let's say you got a special person in your life. And you say, I want to buy you some diamonds. Multiple. I don't know why. You're buying multiple. And you want to know, you ask your friend, well, how much does the average diamond cost? So you go out and you look through some catalogs. And you look at 25 diamonds. And I probably need to do a bigger sample because it's very skewed. 50 diamonds. You spend a little more time researching diamonds. You got it. We got that coming up here next. So does that make sense? You went and looked at the price of 50 random diamonds. It's a rock. It's worthless. I don't know. You could use it to cut some windows. You could do right there. So, Andrew, you went and looked for 50 random diamonds. Does that make sense? You went and spent your time. Here's your 50 random diamonds. And you really want to know what the average price of a diamond is these days, right? So you did your research, you looked through, there's De Beers, all different things, all these things. Let's go here and go to Analyze Distribution. And look at this. Here's the distribution. Now this is pretty skewed, but we have a very large sample size, so the distribution of the mean will be nearly normal. Now your friend says to you, I think diamonds cost on average about $5,000. What would you say to them about that belief? Would you say, I accept that, or is that seems possible? What sounds a better way of phrasing it? Or would you say, I reject that, or that doesn't even seem possible, or I accept, I don't know. What would you say to them? If your friend says, I think diamonds cost about $5,000, What would you say to them? Seems possible. Another friend says, I think they cost about $4,000 on average. Like, I think the average diamond is about $4,000 these days. What would you say to them? Ooh, likely is true. Yeah, we'll see that in a second right here. Charles, good answers right there. Charles, we're throwing you some 500 points too. Charles, that's great answers. What about your friend who says $4,000? I think it's about $4,000 for diamonds these days on average. Still between the intervals. Still seems possible, right? Another friend's like, I think they cost $3,000. And what would you say to your friend who says they cost $3,000? You say, I don't, $3,000? You think 3,000? That's a little, no. I can't, I reject that value. I don't think that's true. I'm not saying it's false. I'm not saying that I know it's false. I'm just saying I think we have evidence against that. From my sample, I believe the average price is somewhere contained in the interval. The true average price of a diamond is somewhere between about $3,032, not including 3,000, to $5,563. So if you look at what happens when we do the statistical test, we can go here to test mean, and we'll do all the test. Test mean of 4,000, or we'll do them in order of the values, not the order of which we did the test. Wait, yeah, 5,000. Okay, 5,000. Test mean 4,000. And last but not least, test mean 3,000. Okay. Here's our statistical test going in order. Can I zoom in? Okay. So going in order of our statistical test right here, you'll notice that the value of 5,000 hypothesized seems likely given our sample results. So given the mean is true, what we observed, given this is the true mean, like we're saying, we think this is true. Your friend said, I think 5,000 is true. What we saw in our sample data seems likely. That's what Charles was getting to. I don't want that time. Seems likely given the null is true. What we saw in our sample seems likely given the null is true. Now, your friend who believes 4,000, what you saw in your sample seems likely given 4,000 is true. Because notice this distribution right here is centered at 5,000. It might be hard to tell, but that's centered at 5,000. This is centered at 4,000. This is centered at 3,000. And the red line is your sample result, which is in the same spot. It looks like it's in different spots, but it's on the same part of the curve. It's at 4,300 in all points of the curve. Best thing to do is a ring pop. Hey, man, you can't eat a real diamond, but you can eat a ring pop. And they got watermelon ring pops. So I'm just saying, you give me a few watermelon ring pops, I don't need diamonds. I'm good. I'll eat the watermelon ring pop. Blue raspberry ring pop, cotton candy ring pop with blue raspberry. Some good ring pop. So your friend over here who believes 3,000, well, that does not seem really likely. And notice that the p-value right here is slightly below because 3,000 was slightly outside the interval. And we can use the interval to use a 5% alpha level to reject it. So it would be rejected. Now, what's really interesting and really cool, who knows the p-value of the two-tailed test? And before I hit enter, I want you to tell me it, because watch this magic. Now, I'm going to enter in a value, and I want you to tell me the p-value down to 4 decimal places. What is the p-value? This is the last part of this we'll do, then we're going to do some 320. What is the p-value of this? Now, I want you to tell me, do you reject that or not reject that? And think about how much you reject that or not reject that. So there's what I am hypothesizing is true. So think about what will happen when I use that value right there. First off, do you reject that, yes or no? Yes, I reject that. No, I do not reject that. And think about how we can use an interval to reject or not reject. Do you reject it? What do you think? Would you reject that value? Why or why not? No, you do not, because it's in the interval, right? It's just barely. It's on the edge of believability. You do not, because it's on the edge of the interval, right? It's still in there. It's walking up to the edge and leaning over and being like, I'm still in here. I'm breaking the green screen. I'm still in here. So it's on it. It's on the line. So when your kids walk up to the line, Kayla, and they're like, I'm in the line. I'm still in. You're like, you like to bend the rules, don't you? This thing does. So think about this. It's just barely to where you not reject it. What's the p-value? So the answer to the question is, it's just barely. Kayla, you're super close, but do remember we only reject for p-values less than alpha. So it's you're right there, but we reject when the p-value is less than alpha. So this is just barely to where we don't reject. So what would the p-value be if it's right on the edge of the interval? Well, Shreya, that would be reject. That's going to reject. That's p-value. So that would be a reject. That'd be something outside the interval. That has to be outside the interval. So you just barely don't reject. You would just barely not reject this. So the p-value of the two-tailed test will be exactly... Watch it not work. I want someone to say it. Oh, we're on top chat still. What am I doing with my life? Shreya, 100 points. We need 30 more than that, Shreya, in a moment. There it is. You're right, Shreya. It's exactly 0.05. Because it's exactly alpha. Because if the p-value is at alpha, we would not reject, because it's right on the edge of believability. So it's right up to where you would not reject. Does that make sense? Because it's, no worries, this is good practice. It's good theory stuff right here. It's not less than alpha. And you notice how it doesn't put the little star on it? It puts a star if you do reject. So the two-tailed test right there, it's right on the edge. And then you could do something where you just barely reject it. So we could take a value that's a little bit outside of it. Like now if I put... This one will be... Notice how it's just barely... I didn't put the decimal. It's just barely below that, like just barely. And take a look. Actually, even due to the rounding, it's below 0.05, but it rounds up to 0.05. So this, in terms of decimals, is so close to 0.05, but it's mathematically below. That's weird to see. I don't think I've ever seen that before. But that is below 0.05, hence it gets the star on it. Even though it's saying 0.0500, it's just barely outside. If we had to report more decimals, it would show us 0.04999999999997 or something. But just barely outside. The rounding is virtually identical. But this one was on the edge of the interval. This one was outside the interval, just barely. In the interval, don't reject. Outside the interval, do reject. Outside the interval, do reject. In the interval, don't reject. So good practice right here on confidence intervals and tests. Let's do some 320. Time for the work. And Charles, thank you so much. We're going to do your question here a little bit. We played that one so much lately. Let's put this one on right now. And we never listened to Celeste. There we go. 320. Model building. We all ready to go? I've been singing everything lately. There was a game called Getting Over It with like a hammer. Put starting it as the remind me of Getting Over It. I like challenge games. Skill. Fun stuff. This music reminds me of Celeste, another good game. Oh, you climb up a mountain. Okay. Notice how we have RMSE. If you're in 320, you've probably heard of RMSE, the typical missile model makes. We definitely use it when we go into time series. We're going to remove this out. I saw the update for our series. Is there anything new with the update? Yeah, a lot of good stuff. It really integrates a lot better with updating packages better. Ours made some pretty big leaps and bounds in the last 2-3 years, especially when you look at packages and stuff and the ease of use. If you have stuff in your RMD that it hasn't used, it will tell you to download them, which is super helpful. You can also go here to look at the knitted version of your file, and you can use the Markdown editor to do a lot of easier things, like be like, this is bold text. So you don't even need to know how to use Markdown. You can still just, type things and then change it as though you're in a Word document. I think a lot of people don't even know about these features because you don't have to know how to do all the, I don't know how to do that right there. I'm not going to be doing all. Is there a video executive summary project? Yep. I'll put that in the chat here in a second, Emily. You got it. I might have the thing up still. Let me see if I can grab that for you real quick, Emily. Here's the executive summary. Here's where I covered the executive summary, Emily, and I'll throw that link in the chat right here for you. So summary right here, Emily. There you go. There you go. You're welcome, Emily. Anytime. 100 points. Thank you for asking. Using off level. Yeah, we can go in here beyond a little bit. You bet. So let's look at this. Here we go. Use EX7, which is the DC bike demand data set. This is from Kaggle. I think it's a Kaggle data set. Your shiny. Awesome. Yes. Good stuff, Andrew. The data has been cleaned, so you don't have to eliminate rows. Let us build the best descriptive models so we can compare the average between days and particular characteristics. Okay. So we need the average right here. We don't need all this bold stuff. Okay. In total, we don't have library red class going on. There we go. In total, there are 4 quantitative variables, 3 categorical variables with 2 levels, and 1 categorical with 7 levels. And we can see this here visually. When we say levels to a variable, what do we mean? Like this says day. What does it mean day has 7 levels? A lot of people say, what is a level to a variable? What do you mean a variable has levels? Like if you said, well, they're just like if it's a question, like what day is it? The levels would be the what to the, like think about how you would tell your parents, you're like, oh, so your teacher said the variable has levels? What is levels? 7 days, exactly. So the question is, like the variable is the question, what day is it? And then 7 is the amount of answers. So that levels is just an answer to the question of what day it is. So when you think about what a level is, it's just saying that there's like 7 buckets where we have like this was a Monday, this was a Tuesday. It's the category for the variable. Exactly. Great answers, everyone right there, and good practice. So we understand what it is when we say there's 7 levels to this categorical variable. Like the question is, what day is it? That's the name of the variable. And so now we get into some interesting stuff right here. This is where it gets fun. And there's some Kaggle. We should use some tidyverse on this, because I was reading some stuff by Julia Siegel, person one of the people who does tidyverse stuff. I really want to get them in here to interview them. They do a lot of great stuff, the people at R. So if you look right here, what is all possible models? All possible models means we're running how many models? And this is where it gets interesting. Things get a little bit wacky. All possible models. Oh, no, that's you thinking of Julie Ferreira. Julie Ferreira is awesome too. Second time mentioning her today. Julie Siegel is a person who works at our studio. Great statistician, Julia Siegel. Does a lot of cool videos on YouTube. Oh, no worries. So many great statisticians out there. When we say all possible models, how many models are we running? How many models would you be running? It's kind of neat. And I think we could figure this out a few theoretical ways. You're running all of them. Well, the tilde dot puts every variable in the model. But if I were to tell you, think of this. Let's go to your kitchen. Kayla, no leftovers tonight. We're cooking a meal right here. I'm cooking it though. So I'd like for you to consider the following. We have ingredients in the kitchen right now. And the ingredients are, we've got here steak, we got here butter, we got here onions. So I want you to think this over for a moment. How many possible meals are there? Oh, you hate cooking? Oh, I love cooking. You do it at a different level than me, though. You're cooking probably a lot more often. I'm cooking and, I just feed Chelsea and I feed each other. So, there's only one possible meal. You're eating steak, butter, and onions. That's your only meal? That's all you got? You got a lot of options. Kayla, what if your kids you say, okay, look, all we got in the fridge is steak, butter, and onions for tonight. And they say, I don't want steak, butter, onions. You say, well, then this. This is an option. You just have to think through what are your options right here. I mean, if your kid's like, I don't want to eat it, you say, okay, well then all we got is steak, butter, onions. I guess I know what you're having for dinner. Statistics is very much like real life. We don't got cereal in the house. There's no cereal. We got steak, butter, onions. That's all we got. Weird house we live in. All we got is steak, butter, onions. That's all we got. But the kid says, I don't want steak, butter, onions. So what are they going to get? And we have a name for this. What are they going to get? We got steak, butter, and onions. They say, I don't want any of that. So, all right. Nothing. What do we call the nothing model? This is literally the idea of like X1, X2. So what's always, now we're bringing it back to stats ideas. What is the model that you get nothing? Sorry, you got nothing. Nope, nothing. What is the model with nothing? This is an option at all points for us. The naive, Shreya, you got it right there. The naive. The naive has none of our x's. Guess what? You don't like anything, you get in the naive. So the naive model, a lot of naive functions right there, is that you get nothing. Nope. But let's go to the simple world. It'd be weird. There's a pretty good simple option. Someone says, I'm not too complicated, just throw it in the oven. They want the what? Now, this is probably the only model I would consider in this weird simple world. But someone says, you know what? I don't need anything crazy. Just throw that in the oven and just hand it to me. That's all I want. So we want to go to the simple world here now. The simple world. What are they going to eat? Well, not like they were all. Think of not partial F. Just this is a model with. Well, so think of this as the food analogy. They say, hey, you know what? You don't gotta do anything crazy here. Just give me a what? Here's their options. This is the dinner options they got. What do they want? Simple model. 1x variable. Simple model means 1x. You say, hey, just give me the what? Just put it in the oven and give it to me. I'll take the steak. So we could make a model with x1, right? And then when your weird kids, probably Brian, says, you know what? I'll eat the butter. Probably not Chelsea. She doesn't like onions. Says, I'll eat the onions. So, but if you're making dinner for this for your kids, do you have to do it this way? What would you want here? This is simple regression. We have a model with just steak in it. So there's an x1 model, a model with just x2 in it, a model with x3 in it. What might you want? You might choose the big model. You might want it all. I don't know. What's your choice of meal? Kayla wants the full model right here. Everything, all of our x's. So that's what Kayla wants. Anyone here not a fan of onions? Because then maybe you want a model that would be this right here. Maybe you're weird and you just like grilled onions. So you want a little butter on your onions. But so there's your choice of model. What is the only model I'm missing out? You can name it by its food counterparts or what is the only thing? Maybe you're on the keto. I don't know what kind of diet this would be. But the only model we're missing out right here is what? The only model we're missing out right now is what? We don't have any potatoes in the house. Sorry. I should have put potatoes on there. It'd be like a bigger example. We'd have to do a lot more permutations of the results. What is the only model we're missing out? You can name it by the variable types, but there's one model missing right now. One model missing in this example. Steak and onions. Yep. So that'd be x1, x3 by virtue of the names of the variables. 1, 2, 3, 4, 5, 6, 7, 8. Correct. Good. Seems like a lot of work, right? What if I told you there's a super quick way to find out the answer? The answer to this is how many x's are there? Just not a trick question. How many x's are there? Not a trick question. How many? There's 3 x's, right? So if there's 3 x's, 2 raised to the third is 8. That's how we can find out that there are 1, 2, 3, 4, 5, 6, 7, 8 models. So let me ask you this. Quantitative variables introduce how many coefficient estimates to the model? Don't think too complicated. I'm not trying to trick you with this, but if you have a quantitative variable like height, that gets how many coefficient estimates? These are the easy ones we used to do back in the day. It's just like, how many coefficient estimates would a quantitative variable put into the model? How many estimates would it put in to estimate the weight of it? It put in 1, right? So would you agree that each quantitative is going to add in 1? So if we have 4 quantitatives, how many estimates would those have each? Like they could add in a potential of how many estimates. If they each add in 1 and there's 4 of them, then that would add in how many? Not trying to be tricky. 1 each, so total of 4, right? Does that make sense? 4 total. So 1 each, 4 total, because each one does 1. Now this says a 2-level categorical, which you can see right here. A 2-level categorical creates how many indicators when creating a model? If a 2-level categorical is added to a model, how many indicators would it have? Because remember, we have a reference level and then we have the remaining are indicators. So a 2-level would put in 1 indicator. So all the 2 levels here are going to introduce 1 indicator. So how many total will we get out of this? Because there are 3 2 levels. You can see them right there. So since each 2-level indicator introduces each 2-level categorical variable introduces 1 new indicator, there'll be 3 total. But here's the weird one. There is 1 7-level, and the 7 level will introduce how many? And we could show the math right here. The 7 level is going to introduce how many? The 7 level is going to introduce how many? Ooh. I hate that it does that. 6, exactly. It's trying to be nice and like thinks I'm trying to do notation. So the 7 level introduces 6, and there's just one of these variables. So the first number is the amount. The first number I've written is the amount of variables you have. There's one 7 level variable which introduces 6 coefficients. There's 2. Nope. That's why I gotta check your math. There's 3 2 levels that introduce 1 coefficient. There's 4 quantitatives that introduce 1 coefficient. So with this, be careful. Check my math. I'm gonna check it too. How many total x's are possible? I think we might have just enough time, Cassandra. Good question. We did it earlier today, and we did it last night too, if you want to check it out. So good to see you here, Priya. Got a question. Well, so yeah, don't worry, double check your math. I'm gonna delete this 7 over here. So how many total are introduced? 13. So tell me the mathematical answer to how to figure out how many possible models could we create from this. So 13, and 13 is found by going 6, because that's 1 times 6 is 6, then 4, so you're just adding these up. Correct, that's correct, Shreya, right there. And so Shreya has done the math correctly to figure out how many total x's there are. Now that we know how many x's there are, what do we do now? So use this example here to say, well, since we know how many x's there are, how many combinations of meals could we make from these x's? Because we're just saying we got here 13 different items. We got potatoes and butter and onions and mushrooms and steak and lettuce and I don't know what else and Jello. That's it. There's the answer. Yeah, Priya, we might have just enough time. We'll take a look. Does that make sense? And there's no interactions yet. Oh, the interactions. Well, if we did interactions, then things get a little wacky. Does it say to do the interactions? Because even I'm going to have to cheat to look that up. If we run all possible procedure without interactions. So this is not the interactions because there's no interactions right here. This is just x1, x2. And then if we were to include an interaction, it would look like this right here mathematically. It would look like that. Does that make sense? That's the x1, x2 model with an x1, x2 interaction. Does that make sense, Kayla, right there? We haven't considered this yet because I think it might do that later on. That's where things get really wacky, and I have to double check that equation because I don't use it very much. It's a little more complicated. But without interactions, the way to figure out how many models there are is to figure out what. We have to figure out how many whats there are that we're working with here. If we want to figure out how many models there are, like possibilities of models, possibilities of meals, we have to figure out how many whats there are. Yeah, there's 8,192 different possible models, and we figured that out by knowing how many whats there are. You first need to figure out, which is what this problem is trying to teach you through, you first need to figure out how many whats there are. How many x's. Once you figure out how many x's, you just do 2 raised to that, and that will figure out the combinations of possibilities, including the naive model. So you could always just not use anything. You can say, well, you don't get any food. But you can always do the simple models or all the way to the complex and do permutations of the variables within. So it's important to know that when you're doing this, first step is figure out how many x's are you dealing with? How many coefficient estimates? And the hard one here is indicators. Because if you have a 7-level categorical, then one of them becomes the reference and the remaining 6 are indicators, meaning there's 6 things that could be coefficient estimates that could be part of the model. You would have to break model hierarchy to use like 4 of them, but sometimes we do that. Is that a good start? Let's look at more. Run reg subsets, come see with model set at the lowest AICs. It's not long. We did a good part of that right there. Let's do a little reg subsets. Then we'll do more tool 1 right here. Okay. Let's run some reg subsets. I haven't run reg subsets in a while. Okay. So what does reg subsets do? Reg subsets, I think we got to use method exhaustive, right? I like reg subsets, but it's in the leaps package. It's an older code. We need to update. This is why I was debating the whole Julius Siegel thing, because I'm like, we should update it. Demand tilde what? Run reg subsets and see the models come up with a set of models with the lowest AICs. Good stuff. Reg subsets, I think, uses method exhaustive. I'm going to even check the documentation on it. Here it is right here. I don't use that format. I use the formula format. I don't remember learning these functions. It's at the very end of class. Very last part of 320. Very, very last stuff. To force in. We don't want to force anything in. Method exhaustive. There it is. I think it does method exhaustive by default. Let's go to example code. If you go to the very bottom, reg subsets, there it is, fertility dot. N best, this reports the number of best. So we should be fine. Y tilde x comma data equals. And then Petrie did the C models. Oh yeah. Is that the problem right there? And then data equals. We're doing the X7 byte data set. Y tilde x comma data equals. We didn't store the, yeah, cool, it's using exhaustive. Let's put it into models. Store it into the object models right there. It ran. And then Petrie created, I believe his code is here, the C models. That's in reg class. Good. And we're going to go right here, report our models, and let's take a look. Nice and easy. And let's take a look. Okay. So here is, did it say run with or without interactions? Do not consider interactions. Good, good, good. Do not, okay, didn't change anything. Cool. Okay. What is this output telling us? Google says to identify different best models of different sizes. Oh, cool. Great job right there, Shreya, helping out. Great stuff. So when you look at this output right here, what do you think is the most important thing to know what the value of it means? If you look at this output, we got right here the number of vars. That probably means number of variables. All these things right here. And then you've got the variables, which are in your model. But what do you think this is? What do you think that is? What do you think that is? Yeah, he's Googling it. I'm Googling someone very important. What do you think that is? Does anyone know? That is the Ake-Ike information criteria. Ake-Ike. So Hirotoga Ake-Ike was a famous Japanese statistician, and his paper on AIC, Ake-Ike's information criteria, that's what the A of AIC stands for, is used for model selection. So this guy, this gentleman right here, he's also the mentor of Humphreys Bosdogan, who is a professor in our department. We actually had a celebration at UT. He sadly has passed. I mean, he'd be close to 100 years old now, but great, great man. Is metric used to compare the fit of a model? Exactly. Shreya, great job Googling these things. Yep. AIC, Ake-Ike's information criteria. There's also AICC, which is his corrected information criteria. And it's pretty easy to understand what's going on with the AIC. All you have to know is lower AIC is better. That's like the number one most important thing to know. So how do you notice this output right here is organized? It's organized for the whatist AIC. Andrew Wind is the best. It's organized for the whatist AIC. How did we organize that output? This is the first, probably most important thing to know about AIC. Of course, I'm not going to delete that. How is this organized? By model 1, model 2, model 3, model 4, model 5. Lowest, right? So it's telling you that's your top choice. So the lower the AIC, the better, right? But then, what do you notice right here? The number of variables. Let's say you go to a restaurant and they're making you this dish with like 50 ingredients, but all you really want is a steak. What might you do when you get the extra 49 ingredients? You might just be like, I just want this steak. That's how I eat steak. You just like, I just want steak. That's all Brian wants today. When we make models, a lot of times we want what amount of variables, more or less. It's a good way to protect against overfitting. Well, we want to use training and validation with overfitting. Toss those extra ingredients. But maybe they really help. Maybe it's like in some sort of like béarnaise sauce or like shiitake mushrooms with some portobellos. It's got like a mushroom sauce with a demi-glaze or something. He uses some nice French words on it. Someone said, attends, Oh no, they said some French words over it. So we generally actually want models with less variables. Like usually we want the world to be as simple as possible. Just think it'd be easy if I said my company's profits are explained by this one variable. Wouldn't the company love it if I said like, hey, the amount of people who go to our website explains everything about our profits. All we need to do is just focus on getting people to go to the website. And they'd say, that's great. And then we get people to go to the website and they're like, well, our profits didn't go up. And I'm like, well, it's also like, what they see when they go to the website. Okay, so we need a good front page on the website. Okay, well, we made the front page. I say, well, it's also, what time of the day they're visiting the website too. All of a sudden now I keep adding more what's and what's to their world. I keep giving them a new what every time I say, well, it's also what time of the day they're going to the website. It's also what version of the website they're seeing. Oh, it's also what their socioeconomic status is. I keep giving them more and more what's. Like I keep giving them more and more X's. So the company's going to be like, gosh, this is getting so complicated. Unfortunately, the world is often complicated. Like we'd love for the world to be simple. So what we have right here is our competing models. And probably, what models would you be debating between right now? If you just look at this output, and with what I just told you right there, would you debate between model 1, 2, 3, 4, 5? What are your top models right here? Hint, they're organized properly in the order they're given to you. What models would you probably say? And technically, you can consider all of them for any statistician watching. Any model could be right. All models are wrong. Some are useful. 1 and 2. Why is 2 under consideration? Like 1 is the best. It has the lowest AIC. That's the best, but I don't know. Maybe we should use 2. Shreya, why are you considering 2? Because why? That's the exact right answer, Shreya. They do have both of these are the lowest AIC. That is correct. But why did you say maybe we should take a look at 2? And management might want a certain variable in the model. So management might want model 4 for all we know. Less variables, right? That's generally a good thing to have is less variables. So model 2 might be a good one to consider. Last note on AIC, then we're going to switch back to 201 right here. Here's your cutoffs for AIC. Oh my gosh, I'm losing my little thing on my chair. That's close enough. So models within an AIC of 2 are virtually identical. There's no, like, what if it's 2.1? Basically the same. What if it's 2.8? I don't know, it's still kind of the same. Models within an AIC of 2 are virtually identical. So almost all of these models, except for the last one, are virtually identical. AIC is just an estimate of how close you are to the truth. We don't even know what the truth is, so we just estimate that we're this close to the truth. It's a guess. We don't know what the truth is. How can we estimate how close we are to the truth? Well, a perfect model would have a r-squared of 1, so we can look at kind of what we would expect the truth to be and then create estimates of how close we are to it. Like, estimate how long till you get to my house. Well, you don't know how long it'll take. You're just estimating. You're just guessing. That's what we do in statistics, so we make good guesses. So all those models there are technically identical, but in truth, as Shreya said, I'd probably be in consideration between model 4 and model 1 and model 2 with the 4 and 5 variables. This model is a bit different, and an AIC of 10 is very different. So those cutoff, still in Texas, probably like 14. Yeah, about right. Take some rest stops between. So here's the big note to remember: AICs within 2 are virtually identical. AICs within 10 are pretty different. And between 2 and 10, I don't know, kind of different. With that, we're going to do some 201. Let's head back right here. Think we got time for Charles' question? We got one more, maybe. Charles was underwear. Oh, no. Let me grab it right here. Great stuff. Did that help out, Kayla? That's a good bit of the assignment and a good bit of lecture. I should have marked Charles. Oh, here it is. Define the parameter proportional and write the null clause. Yes. Define the parameter, write the... Okay. Let's see. Define the parameter. Here we go. Found it. You're welcome, Shreya. You got it, Charles. Thank you, Charles. 100 points. I appreciate that. Stat 201. Take the... Nope. We do the timestamp afterwards. Chapter 16 quiz. Null and alternative. All right, let's go knock another home run here. Here we go. Bye, Shreya. Have a good evening. Okay. So whenever we write our null and alternative, probably the best thing to ask, see, Kayla, is in class? Probably the best thing to ask when we write a null and alternative is, are we dealing with categorical or quantitative data? So we have some notes from earlier, I think right about here. So here's our notes from earlier on this. And when we do the null and alternative in statistical notation, there's basically 3 questions. And I've kind of got it grouped right here. We'll put question number 2, question number 1, and question number 3. Let's think about this as 3 questions to help us solve this. Now, why do we not ever ask the sign of the alternative? I mean, of the null. Why do we never ask the sign of the null? I'm speaking specifically about this. Violin randomly plays. Why do we never ask about this? Why do we never say, what is the sign for the null? Why do we be like, oh, we don't got to worry about that. The null always has the equal sign. Priya right there, 100 points. You got it. So the null has the equal sign. We got that. So we could ask, there's in any way you want to do the order of the questions. But the first question right here would be kind of, what are we testing? Like, this is the idea of what are we testing. The null has the equal sign, so whatever we put for the something, it equals something. So how would we figure out if it's mu, which is going to be mean, p for proportion, or the difference between 2 means? How would we figure this out? We got to set ourselves up for success and be like, well, how are we going to figure that out if it's mu, p, or mu1 minus mu2, which is the difference between 2 means? How would we figure that out? Because that's what we're going to be dealing with, mu and p in this problem. How do we know if it's mu or p? How are we going to figure that first part? Mu is quantitative. Pre right there, great answers. Mu is quantitative. So we know mu is quantitative and p is going to be categorical. It's that cat versus quant. So we got to ask, are we doing a question where it says, like, what is the proportion or what is the quantitative mean amount? A casino wants to know if their slot machine really is this amount of wins. Now, the way to do this is to ask the question to someone, did you win? So they want to know if it really is a win out of 7 out of 100. Now, does that sound like a quantitative? We're not saying how much you won. We're asking, did you win? Is that quantitative or CAT? So Q or C in the chat. We're asking someone, did you win from the slot machine? Is that a quantitative or categorical question? It's categorical. Did you win? So just think about how you'd answer it. You'd say, yes, I won. And you'd be like, oh, that's awesome. So that is categorical, making it proportions. The only answers to these questions right now are mu and p. P hat and x bar are not population parameters. So p is the only answer, and p is for proportions. So good stuff right there. And it's not a p-value. It's not p-value. That is proportion, like the proportion of people who win. So that means this goes right here. As soon as you select that, that goes right there for all those. We've answered multiple blanks. Now we know the null always has the equal sign right here. Now the only other thing for us to figure out right now, it gives us the hypothesized value that they're testing against. So we don't have to worry about this one right here. This is the hypothesized value you're testing against, but we have to figure out the what of the alternative now. So question 3 I've worded on here is the what of the alternative. Well, that's a proportion though. I know it looks quantitative, like it's a number, but that means 7 out of 100 people said they won. So always go to the question. I think a lot of people say, well, that's a quantitative value. And I'm like, but how would that data be collected? Because to find 7 out of 100 people won or what they expect, you'd have to walk up to people and say, did you win? And then you could summarize it, because 7 out of 100 could be expressed from a sample as what? So Charles, think about 7 out of 100 as 7 would be this and 100 would be this with notation, or someone else can answer. Good work. And then you'd be like, oh, that is for that kind of data because it's something over something, right? So, which would then give you, if it was from a sample, would give you this. Remember, you're asking, did you win? And then there's successes and failures. Like, I won, success. It'd be percents, and 7 out of 100, if it was from a sample, would be X over N. Does that make sense? So that's the amount of samples out of or amount of observations that are successful out of a sample size. So once again, confirming it is categorical. And we want to know if it really is, and that's what people were talking about with the sign right here. We want to know if it really is 7%. So it either is or is not. And notice how these are greater than or equal to. We never do that. Less than or equal to, we never do that. Null has the equal sign. So that has to be the answer, just by process elimination. The next one says people are spending that much on a company website. They want to know if it's decreased. So we could start off here with the sign. The sign indicates the way the alternative goes. So just drop it in the chat right now. What way is the sign going to go? We're starting here at the end of this one. The sign of the alternative would be what? They have a hypothesized value of $28 over here. That's the hypothesized amount, what they're testing. And then Priya, great work right there. The sign is less than because the question they're asking from the researcher always decides, not the data. Researcher decides which way the sign goes. Great job, Charles. 100 points. The null has the equal sign, and we are testing quantitative or categorical. Walk up to someone and say, how much money did you spend on the website? If they say $10, it's quantitative. If they say yes, it's categorical. So is this C or Q? How much money did you spend on the website? Great job right there, Priya. It is quantitative. That means we're testing the true mean. Mu stands for the true mean. Quantitative, which means we're dealing with means, and mu goes right here. Next, we have a pharmaceutical company is wondering if people are cured by their drug if it's greater than 40%. So you'd need to walk up to someone and ask them what. How would you collect data on this to find out if people were cured? So it might be a lot to type, or you can answer the question. But think about what we've been doing right here to think, okay, 40%, that's a number. Careful, I'm trying to trick you right now. Because you want to ask the question instead of looking at it. Are you cured? 100 points right there. So the answer would be yes or no, right? Yes or no, so categorical. So that's proportion of people who are cured. And so it's the proportion of patients cured by the new drug, not the mean, because we're just doing the proportion of people who are cured from this drug. So that puts this here as P. We know the null has always the equal sign, and they want to know if it's greater than, clearly making the alternative the greater than. Next, a bank believes the percentage of customers using their website is this. The bank wants to know if it has changed. Cool. They want to know if it's changed. So if you ask somebody, do you use the website? That'll direct you to if this is proportions or categorical, because that's how the bank would have to collect data. Is somebody using our website? So categorical or quantitative? Is somebody using our website? C or Q? So you go say, are you using the website? Categorical, yep. Proportions. And the proportion. And now we go P. And equals. And has it changed? So make sure to follow yours. This one says changed right here. So you can even kind of make sure, you can kind of cheat. If you highlight everything, you can see which text are the things that change. There's the hypothesis value. It says different. Yours says different. So that'd be the not equals. Exactly. Great job, Charles, right there. Good practice. The question, the researcher, whoever's doing it, indicates the sign of the alternative. That's got it. Well, let's see. Is anyone here? We might try to do a quick one. Might do a speed run of something. We're probably doing a lot of chapter 17 tomorrow. Oh my gosh. We're going to get through all of chapter 17 in lecture tomorrow. So it's going to be quick. Well, not quick, but you know what I mean. Whew. We got chapter 17 and 19, and it's very similar. It's very similar. There's a lot of problems that are basically the same. Chapter 17 homework. We can do some chapter 17 homework tomorrow, and maybe I'll even do another stream for it. I'll see. We'll see. But no, I really want to make sure. I want to say thank you, because I dare you to speedrun the single response. Which one's the single response? Which one? The multiple choice? The true null hypothesis. Oh, we got to put the timer on. Got to get the timer going. Last, you got this. You got this, Zach. You got this, Zach. Okay, here we go. What error is made when the true null is rejected? That's a type 1. When the null is true and reject it. What type of error is made? Well, that's a type 2. When the null is false and we fail to reject it. What's the probability the test correctly rejects? That's the power. Correctly rejects the false null. It's power. Threshold, that's alpha level right there. That's when we reject the null as the threshold. P-values, what should you include? P-value lower than level of significance, reject the null. P-value is low, reject the null. Which of the following is correct interpretation of P-value that's not small? What we saw is not surprising. We fail to reject. Which of these is an error? Null is true, we reject it. That's an error. Null is false, we fail to reject it. That's an error. Those type 1, type 2 are type 1, type 2 respectively. What is the name of the difference between the null? That's effect size, and the truth, that's effect size. Is that all of them? I think it's all of them. Oh, dang it. Sub 1. Here we go. Make sure to review those. That's speed run of those right there, but just commit them to memory. Like, a lot of those are definitions, Hey, I should have hit stop earlier. I lost some time on the finishing it up. And we have videos on the other things. I go through more details in the video last night. I think that's all the single questions. Watch me find another one over here that's not on that. If you're looking for these other questions, we did them last night. We also did them earlier today, so check those out. I might be able to speedrun this question. 8%. No. Oh, no. Dang it. No, it'd be a little tighter. What percent? 95? Oh, well, that's not right. Oh, man, it's got to be around here. Really? Really? When you can't? Is it really just going to be this? Last try. I'm going symmetric. That was close. That was close. Just guess in the interval. From my knowledge of doing that problem a bunch of times. Usually the margin of error is about 2-ish%. So I went symmetric up and down. So the margin of error is 1.8%, but just guessing at it. Don't guess at your homework. Yeah, we did the random poll, I think. Was it the politician poll question? That's a similar type. I think we did that one earlier today. Let me look at the timestamps. Presidential approval rating. Yeah, the presidential approval started office hours at 7 minutes in. 700 with 800. Okay. 800 with a random sample size of 51. That's going to be like a margin of error. It's larger margin of error when it's that. It's going to be like a margin of error about 3%. It's margin of error. So they want to... Well, yeah, we can't reject that. Oh, it's way off. A little smaller margin of error. Nope. We're not guessing this one well. Really? It's a bigger margin of error? Guess it is. Sure, why not? 2 more guesses we got in us. Done. And so check it out. We worked through, so sub in on that one. So I think we worked through that one right here. So this was the presidential approval rating right here. Just understanding what your answer should look like, the symmetry. I have to go here in a second, class starting up. But we went through, we marked all the notation. So as we just mess around here at the end, but make sure to mark your notation, go through, understand how to get the z-score and such. But margin of errors are usually pretty similar. Like, I think this might even literally be identical. Is it the same answer? Was that literally the same question? 47.5. Yeah, it's the same margin of error. Oh, because look at this. 5248. Very similar. Very similar numbers. Very similar margin of error. Well, that's got it. With that, we'll be back tomorrow. Time for class here in a moment. Bye for now. Whenever real quick, class in 15 minutes. Bye, everyone.